Good morning, everyone, and welcome to day two of our Encryption Consulting Virtual Conference 2024. Kicking things off today, we have Thomas Gustafsson, Chief PKI Officer at Keyfactor. Thomas will delve into the exciting developments in quantum safe cryptography, FIPS standards, and updates to PKCS 11. He'll also provide fascinating insights into the performance of new algorithms like ML-DSA, comparing their speeds and effectiveness. This is going to be an insightful session for anyone curious about the future of cryptographic standards. Please welcome Thomas.
Hi, my name is Thomas Gustafsson. I'm the Chief PKI Officer at Keyfactor, and I've been working in the PKI and applied cryptography space for, well, something like 30 years now. And for the last couple of years, I have been working extensively implementing quantum safe cryptography in PKI and digital signature systems. And I'm here to share some of my experience on using hardware security modules with the new quantum safe cryptographic algorithms. So I will assume that most attendees in this conference will know the background story on quantum computing and why we need quantum safe algorithms. So I will just do a very brief introduction or recap, if you will. So we'll know that quantum computers is coming. So they're being developed today by tech giants and nation states. And the interesting thing is that quantum computers have moved from a research area into an engineering discipline, which means that there is now a roadmap by the constructors of quantum computers how or when they expect to be able to create what is called a cryptographically relevant quantum computer. And this means unacceptable risks, since a cryptographically relevant quantum computer will be able to crack or break the asymmetric algorithms that we or the whole world relies on today. And that is why we need new algorithms. And lucky as we are, new quantum safe algorithms have been standardized this year in August 2024. And with these standardized algorithms now in place, it is time to start to make the transition to quantum safe algorithms. Because we know that such a transition will take a long time, and it's better to start as soon as possible. So it is a bit of celebration time for us who have been working in this space for quite some time now, since we have moved from the draft or suggested algorithms, which were very cool names like Kyber, Dilithium, and Sphinx Plus, but they are now standardized in the form of ML-CAM FIPS 203, ML-DSA FIPS 204, and SLH-DSA FIPS 205. So this was a big moment there on the 13th of August when these new FIPS standards was released. And also want to highlight that it's time to ditch the old names and start using the new ones, ML-CAM, ML-DSA, and SLH-DSA, because dilithium is not the same as ML-DSA. So if you want to know what we're talking about and be able to interoperate, we should use the same names for the algorithms, because if you try to sign something with dilithium, you will not be able to verify it with ML-DSA. So celebratory. So the old background, as many of us know, is that the world has been working on this since 2016, when NIST called for quantum-resistant cryptographic algorithms in what is called the PQC contest. So during that time, a lot of algorithms came put forward. And in September 22, NSA released what is known as the CNSA 2.0 directive on post-quantum adoption. So this is currently pretty much the only fixed timeline we have for migration to post-quantum algorithms, which states that sometimes around 2030 or shortly thereafter, we should have switched to post-quantum cryptographic algorithms or quantum-safe algorithms. So there was a draft period, and there was starting to implement things. And the final moment, 13th of August, just a couple of months ago, the standards were released, as I mentioned. And now we are in November 2024, where everyone is scrambling to finalize the implementations of the standard of the FIPS, final FIPS standards. So this is where we are right now, and things are happening very fast. So, to getting a little bit into the algorithms before we jump into practical experiences. So we have now available these NIST standards, ML-Chem, ML-DSA, SLH-DSA, which are the most generic key encapsulation methods for key exchange, and digital signature algorithms, which are DSA. We also have two so-called stateful hash-based signature algorithms, LMS and XMSS. But these are, well, as mentioned, stateful, which means that they are quite impractical for generic usage. Might be used for some specific use cases, but not generically. So they're because of that, we focus on the more generic ones, in particular ML-DSA, which is a kind of primary choice. NIST has also promised that they will deliver soon, at least during 2025, a FNDSA, which is also a new signature algorithm based on or derived from what is currently called as Falcon during the draft phase. There will also come some new key encapsulation methods, probably HQC and BIKE, which is part of the round 4 of the NIST post-quantum cryptography contest. But the world is not only about NIST even. So there are also other bodies which are looking at standardizing some other algorithms. For example, BSI in Germany is looking to standardize the usage of classic McEliece, which is also for some specific use cases. They are also looking at, together with, or in the ISO context, standardized FrodoChem, another key encapsulation method. OpenSSH has gone through IETF to standardize their usage of SN-True Prime. And there's also a word that Nippon Telecom is standardizing N-True for some use cases. So there is not everything about the NIST algorithm, but still, say, when we're going to dig into HSMs, the NIST algorithms are definitely the ones that will be standardized and implemented in HSMs right now. So if you're looking at other algorithms, you should probably expect some turbulence. So putting these algorithms into use, there are different efforts. So the main efforts are oriented in two directions. One is to standardizing techniques and adaptations for migrating from classic asymmetric cryptography, RSA, EC, and DSA into the new quantum safe algorithms. And the second one is changes to protocols and message formats to tweak them or to accommodate them for the new algorithms. And some accommodations particularly is needed for the key encapsulation methods, as they don't work in the same way as RSA and Diffie-Hellman for key exchange. And also these cannot be used to generate signatures, which actually have some consequences. So just to mention a few of these efforts when it comes to migration are dual key certificates, which is standardized in X509, as also known as hybrid certificates. But there is also some other efforts going on for other formats of hybrid certificates, such as delta certificates or composite signatures, which are still in draft. And there's also things like a certificate binding, which binds one classic certificate into together with a post-quantum certificate. And also want to mention things like the X9, the Financial Standardization Organization, is working on, for example, X946, how to use TLS together with dual key certificates or together with two certificates with different types of algorithms. And to mention some of the changes to accommodate, say, CHEM specifically, there has to be an extension to TLS in order to use key encapsulation mechanisms instead of RSA or Diffie-Hellman key agreement. So this is coming. and also changes to CMS messages in order to encrypt data or create what is called as envelope data using CHEMs instead of RSA or EC Diffie-Hellman. Also interesting things are around the corner for certificate issuance, where in particularly things like proof of possession, which is a requirement, or a signature proof of possession is requirement in PKCS 10 certificate signing requests. So these cannot be created at the moment with CAM keys since they are not able to generate signatures. So there is some work going on there, but some other protocols like CMP and CRMF are already agile enough in order to handle this with various techniques. OpenPGP is also introducing signatures and CAMs into the standard. So what about PKI and signing, and particularly when on hardware security modules? So when it comes to PKI and digital signatures, they always use HSMs in production. At least that's my experience, or for all serious deployments. And you can use hardware security modules in a couple of different ways where you might notice some difference with the new quantum safe algorithms, or depending on how you use them. So if we compare to if you just use things in software, like a bouncy castle open source cryptographic API, you will not notice any real difference when using these new algorithms. But when we talk about hardware security modules, you can either use things like soft HSM, which is just locally in memory, the same as a software crypto token. There are also PCI HSMs, such as you would put in an appliance. They are basically the same as in memory because modern operating systems use shared memory access to access the PCI bus, I believe. So it's also very fast and instant. But then we come to network-based HSMs, where all communication with HSM passes the network stack and the wire, which introduces some latency. If it's very local, latency is very low, but it is there. But then we also, the next step is to move to cloud HSMs with even more latency, because then you actually move over the internet in many cases. You can, reduce latency by having a cloud HSM co-located in a close-by data center, but latency might be quite significant. And to dig into the specifics of this, there is actually a reason why the hash and sign paradigm, which we use, for SHA-256 with RSA or SHA-256 with ECDSA, where we hash a message first and then just sign the hash. It's very efficient because the data that you transfer to the HSM is never more than a hash, which might be 32 bytes or in that range. But there is also a reason why hash and sign is legacy, because you can make a bunch of security-wise or cryptographically not so wise decisions when you separate the hashing and signing in the way that it's done with RSA and EC today. So for this reason, the new algorithms have typically gone away from this paradigm. To emphasize it more, if we look at what we are signing, the sizes vary, of course, a lot, right? Certificate is fairly small, maybe a couple of kilobytes. CRLs might be small when they're empty, but they can also become very, very large, tens or even hundreds of megabytes large. Maybe a bank transaction is small. Documents, contracts, PDF documents are kind of small to medium, and firmware are typically very huge, like megabytes or hundreds of megabytes even. And when we dig into the usage of HSM, there is actually a limit how much data you can stream efficiently to a network-connected HSM and still expect it to work well. And some popular options of cloud HSMs out there by cloud providers currently have a 4 kilobyte limit of the signature payload, the data you send in order to be signed. And all the new algorithms were, at least, until the FIPS standards came out, just signed. You were supposed to stream the full data to the signing function or the HSM. So because that has better security properties than the old hash and sign paradigm. But well, with FIPS 204 and FIPS 205, there was introduction of a new hash, pre-hash function. So now FIPS 204 contains ML-DSA plus hash ML-DSA, where hash ML-DSA actually is designed to take or create a hash, which is then run through the signature function. So how would you apply this, for example, in a PKI? So I mean, technically, it's possible to use pure ML-DSA for certificates and hash ML-DSA for CRLs when they are too big. This would be FIPS compliant because you are allowed to use keys generated for ML-DSA to in hash ML-DSA context, but we typically haven't seen this in PKI. So it might become a bit easily confusing, like we've had with the ED25519 and the pre-hash or PH version of ED25519. So this has historically, for use cases using ML-DSA, been quite confusing and led to some problems. So this is something which is how to use these algorithms is something that is currently there is some standardization for it, but it's not 100% completed, and there is a lot of discussion going on in Internet Engineering Task Force about it. And to discuss how it can be done with signing, so CMS or cryptographic message syntax already have it's not a workaround, but it's how CMS works. If you use what is called sign attributes in your CMS message, the CMS specification actually says that you combine the signed attributes and the message and hash it and then sign the hash. So it's done on an application level. But there's also some debate going on which is the most wise way and best security, most secure way to do this. And of course, there's lots of other signature formats which has to be decided how this should be done. So moving on to some PQC in practice. So looking at tests that are being done that we have done with hardware security modules. So we did started to do signing speed testing, comparing different HSMs, in the draft phase, so the dilithium phase of the new algorithms. So where we found out that, at least when the implementations were, say, mature enough, the performance of dilithium on normal powerful HSMs were not bad at all. Could be maybe 10% slower or in that range. And for some implementations, we actually found that dilithium was a lot faster than RSA 3072, for example. So it was even faster. But that was kind of pure signing on HSMs. We also did certificate issuance testing with pure software, in our case, the Bouncy Castle open source cryptographic APIs, which show that compared to RSA, at least dilithium was just maybe 13 to 20% slower, which is completely acceptable since we're still talking about issuing 650 to 700 certificates per second, which is more than enough for the absolute 99.9% of use cases out there. So let's see what's happened now when we move to ML-DSA, because of course we have to do the same thing with ML-DSA. And it's still, unfortunately, a little bit early days, but we have managed to do some testing. So this is initial results with a REST-based HSM over the internet, a cloud-based one, comparing RSA ECP 256 and ML-DSA 44. And it's in this testing for issuing certificates, the performance is exactly the same, which only tells us that it is the networking or things between the application and the HSM which are the bottleneck and not the signature algorithms themselves. A second one, we did tests on PKCS 11 for a development firmware of a local HSM which you install locally. And here we could see fairly good speed. You could issue almost 200 certificates per second with ML-DSA 44, which is completely acceptable for PKI use cases. Unfortunately, for this development or test firmware, the performance of the standard algorithms was very sub-optimized. So you could only see that, okay, it was okay with ML-DSA 44, but you couldn't compare it with the other algorithms. So this is ongoing work still. So I've been promised new versions of firmware and cloud HSMs, during here before Christmas. So we will definitely continue doing this testing, which is slightly early days. One thing that is confusing when you start testing the new algorithms is that some implementations use the names ML-DSA when it was still in the draft phase, which is called ML-DSA IPD, or initial public drafts. So that uses, pre-standard OIDs, and actually the algorithm ML-DSA initial public draft is not exactly the same as the final FIPS 204 ML-DSA algorithms, which means that if you have a library or an HSM that support ML-DSA, but it's the IPD version, and you try to use ML-DSA FIPS standard, then it will not work. You sign it with ML-DSA IPD, and you will not be able to verify it with standard ML-DSA. So this is confusing. It will certainly be straightened out once every implementation has moved to FIPS standard ML-DSA, but at this moment, it can be quite confusing. So if we look at dig deeper into HSMs, there are two major APIs or ways to connect and talk to an HSM. The first is the Oasis PKCS 11 standard, which has been around for many, many years. And I was fearing that PKCS 11 would be slow and take a long time to update for the new algorithms, but they have been amazingly fast, and they have already come out with drafts for a post-quantum update to the PKCS 11 standard. And you will find even on Oasis GitHub, new header files with the new constants for ML-DSA, SLH-GSA, and ML-CAM. So this has been amazingly fast for a standardization organization. And then there are REST APIs where every HSM that has a REST API endpoint uses a proprietary REST API. So you have to look at each specific HSM individually. So when we talk about REST versus PKCS 11, I just wanted to show this picture, what the difference is. You have an application, of course, that you want to talk to an HSM. And if you use PKCS 11, you always need a local PKCS 11 client, which is comes from the HSM vendor that you install on the system, which is so your application talks to the PKCS 11 client, which in turn talks to the HSM. And this is a little bit, when you package your software as, it can be on a server, it can be in a VM, it can be as containers in Kubernetes. Then you have to package a vendor-specific PKCS 11 client, which is a little bit clumsy, and that has to be updated as well. So, you can do it as we typically do it with a small proxy layer and packaged the container, but it's separate maintenance. While on the other hand, for a REST-based HSM, you code that into your application, and it will speak a standard REST API, which most developers know how to code well. So it's quite more easier for, say, cloud native workloads to use. So looking at PKCS 11, this is how it looked like before the FIPS standard or the PKCS 11 standard was updated. Each vendor used what is called vendor-defined mechanisms. So you had to say if this HSM, if that HSM, etc. This code specifically tries to read a post-quantum public key. And then you have to do different code paths for each HSM because they implement things differently and package the values of the public key differently in the HSM. With what will become PKCS 11 version 3.2, which is now in draft, you only have to have one single code out there. So you can look if it's an ML-DSA key, you read what is called CKA value in PKCS 11 language, and then you construct the public key, and code should look exactly the same for every HSM out there which implements PKCS 11 version 3.2. So this is, of course, very attractive from an application developer perspective. And to see what are the changes to PKCS 11. So the signature functions are fairly easy because they are very similar or exactly the same to what we're used to with RSA and EC. You have key pair generation, you have CKM ML-DSA, which is a mechanism for signing using ML-DSA or pre-hash. And it uses the PKCS 11 API called csign, just as normal as we're used to. Key encapsulation methods, on the other hand, require some new things. It still has key pair generation, but it introduces two new key usage flags, encapsulate and decapsulate, where before we had sign, verify, encrypt, decrypt, for example. Now we have encapsulate and decapsulate as well. And there introduces two new PKCS 11 API functions, C encapsulate and C decapsulate. And there will also be a new API for encapsulation and decapsulation in Java 21, for example. So we see there's more application updates to use CAMs than the signature algorithms. And just to show that all the constants which are used in PKCS 11 are already defined. So now there is no reason for any HSM implementation to not use the standard PKCS 11 constant. So you could use the same code path. Very nice. REST-based APIs, on the other hand, looks like, well, typically JSON code to parse you make a REST call, you get a key object back, which is JSON. You can see if it's an RSA, an EC, or an ML-DSA key. And then you get the public key data and assemble it into a public key object. So this is sample Java code for that. So this is also very, easy and familiar for most developers. But the downside is, of course, that you have to do different coding for every different HSM out there, which is, well, it's more work. So to finalize, where are we now? So ACVP testing, which stands for Automated Cryptographic Validation Program, which is a step in the NIST validation program with test vectors where you can verify that the implementation or algorithm is correct. It is stable, so any vendor can do ACVP testing. Bouncy Castle, open source cryptographic API, have been released with a final NIST or FIPS standards for ML-DSA and the other algorithms. There are some other open source tools like Open Quantum Safe project are still on the what is called, which I call the IPD version or initial public draft. So as mentioned, they are not the same as the final FIPS version, which means that you cannot sign something and verify with different libraries. But this will definitely be fixed quite soon when Open Quantum Safe comes out with also the final FIPS standards. Some HSMs I have tested have the FIPS initial public draft. They are also working hard on coming out with final FIPS finals, and I've been promised to get some test versions as early as later this year, whilst other HSM vendors have it in Q1 or Q2 in 2025 to come out with the FIPS standards in their hardware security module. So there's going to be a period depending on which HSM you use. And of course, there will be non-certified versions. So FIPS certification will be, or the HSM vendors will submit their new firmware for FIPS certification during 2025, and that have its time. But at least everything should have passed the ACVP testing before release, which so we know that the algorithms themselves are interoperable between different vendors. And as mentioned, we will remove dilithium completely because it's not ML-DSA, so it's no use of sticking to non-standard algorithms anymore. ML-DSA is what we will use as we go forward. And finally, so of course, the environment is more than, say, PKI and a hardware security module. So when we want to start to migrate to post-quantum algorithm, we have to look at a larger ecosystem. So something we are hoping to be able to do, early next year is to have a PKI that issues certificates to an HTTP server, which some browser can talk to with the ML-CAM key exchange and ML-DSA authentication, and issuing certificates for signing and encryption of email, for example, which also have this specifically. You need ML-CAM for encryption and you need ML-DSA for signing. And of course, having multi-vendor, firmware signing and verification, which is supposedly some of the first use cases for post-quantum cryptographic algorithms. So there's a big ecosystem out there to do interoperability testing with, and these are things that will carry on in the coming months and half a year or so before you can start deploying things in production. So just want to reiterate once that this is just a starting point of a migration to quantum safe algorithms. There will be more algorithms in the future, so crypto agility is definitely a must to maintain in any product that is in existence or in development. So I want to thank you for listening to the presentation, and hope you have a good day.
Unfortunately, Thomas couldn't join us for the live Q&A. However, if you have any questions for Thomas, please feel free to reach out to him directly, or you can email us your questions at info@encryptionconsulting.com, and we'll make sure he receives them. We've got more sessions and plenty of insights lined up, so stay tuned.